Hello everyone, welcome to Reactify Labs. In this video, we will talk about conflict-free replicated data types. Conflict-free replicated data types. And yes, it was able to recognize it in the first attempt. Nice. So there will be a dash here. Okay, so what is conflict-free replicated data type, or what are conflict-free replicated data types? Why do we need them? Where do we use them? The best example is collaborative editing in Google Docs. Collaborative editing. So you must have noticed that while working on a same doc, if multiple people work, right? So let's say A is writing, B is writing, C is writing, D is writing, all are writing at the same time. Everybody sees that, okay, this person wrote this person wrote this, and in the order in which they are written, the same order is displayed, right? It's not like, let's say, somebody writes first and somebody else writes second, then second gets displayed first, or there is some conflict. Even if multiple people work at the same time, still the conflicts don't come there, right? So these all are possible by conflict-free replicated data types. So let's talk about the structure we are going to discuss today. First, we will see the introduction. Okay. Next, we will talk about what are the different types of conflict-free replicated data types. From now on, we will write CRDTs instead of very long conflict-free replicated data types. Next, we will see what are the challenges and considerations. Challenges and considerations associated with CRDTs. And in the end, we will see what are some of the real-world applications. Okay. So this is what we are going to discuss today. And with that, let's start. So CRDTs are data structures. These are data structures designed for distributed systems. Designed for distributed systems where replicas can be updated independently without coordination. Without coordination. Okay. They ensure consistency across replicas by providing conflict resolution mechanisms that don't require synchronization. So CRDTs find applications in collaborative editing, real-time databases, and any distributed system where concurrent updates may occur. So what are the key characteristics of CRDTs? First one is replica independence. CRDTs allow updates to occur on different replicas independently, ensuring that replicas eventually converge to a consistent state. Next is conflict resolution. They incorporate conflict resolution strategies that automatically handle conflicting updates without the need for centralized coordination. And deterministic merge. The merge operation in CRDTs is deterministic, meaning that the order of merging updates does not affect the final state. Okay. Now let's see what are the different types of CRDTs. it might be actually too deep, and you don't need this much level of information. But okay, now that we are discussing, let's see. First one is operation based CRDTs. Operation based CRDTs rely on commutative operations, meaning the order of operations does not affect the outcome. Examples include counters and sets. Okay, so they have counters and sets. So counters allow increments and decrements, ensuring the operation order doesn't affect the final count. Because if, let's say, +1, then +1, then -1 happens, and then -1 happens, the final is 0, right? So no matter what the order of plus and -1 will be, the final count will still be 0. Okay. So that's why the order of operation does not matter and the final state will be same. Next, for sets, it enable adding and removing elements in a way that is commutative regardless of the order of operations. Okay. Next is state based CRDTs. State based CRDTs involve replicas periodically sharing their state with others. Okay. Merging is achieved by taking the least upper bound of the states. Examples include G counter and PN counter. G counter, PN counter. Okay. So state based CRDTs, what they do, the replicas periodically share their state with each other. Okay. And when all these states are shared, then merging is achieved by taking the least upper bound of the states. So G counter is an example where each replica maintains a local counter and the merge operation takes the maximum count across all the replicas. Okay. So each node will have the local counter 1, 2, 3, 4, 3. So for each, like, merge operation takes the maximum counter of all replicas. So 4 is the maximum count. Okay. It means 4 has the latest value. Next, PN counter. It represents a positive or negative counter with separate counters for increments and decrements. Okay. Let's talk more about the G counter and PN counter. So it's an operation based, it's a state based CRDT representing a grow only counter, meaning it only supports increments. Okay. What are the operations here? Increment operation and merge operation. So replicas can only increment operation, it has two operations, increment operation and merge operation. Okay. So replicas can only increment their local counter, and merging involves taking the maximum count across all replicas, ensuring the final state reflects the highest count achieved. And the use case for this is distributed counting. It's useful in scenarios where distributed systems need to maintain a count that can be incremented independently on different nodes. Now, PN counter. PN counter is another example of state-based CRDT representing a positive or negative counter. It has different operations: increment, decrement, and merge. Unlike G counter, P counter supports decrement also. So it represents positive increment, it represents negative increment or decrements, and merge operation combines the counts from both positive and negative counters during the merge operation. And the use case is, it is suitable for scenarios where tracking both increments and decrements is essential, such as vote tallies or resource allocation. Why? Because resource allocation, what happens is, let's say one time you allocate the resource to this and next you may take it out. So this increments, this decrements. So that's why. Okay. Next, let's talk about the challenges and considerations associated with CRDTs. So challenges and considerations. Concurrency control. Managing consistency under high concurrency poses a very big challenge. Concurrent updates from multiple replicas demand nuanced handling to prevent conflicts and maintain a coherent state across the system, right? Because obviously, if you take an example of Google Docs, even 100 people can update it at the same time and still the order is maintained. So the concurrency control is really a challenge. Next, memory overhead. Some CRDTs may incur higher memory overhead. This is a trade-off resulting from the necessity to track causal relationships between updates. While ensuring consistency, it is crucial to be mindful of the potential impact on scalability and resource utilization. Okay. Let's talk about trade-offs. Balancing act in CRDT selection. So what kind of CRDT we need? First one is consistency versus availability. Choosing a CRDT involves navigating trade-offs between consistency of the distributed system and its availability. Striking the right balance is essential here based on the specific requirements of our application. Like what level of consistency we need and what level of availability we need. And next is partition tolerance. Considerations related to the resilience of the system during network partitions is also important. Deciding the degree of tolerance to ensure that the system continues to function even when communication between nodes is disrupted. And as you remember from CAP theorem, we cannot achieve all CAP at the same time. That's why we have a must partition tolerance, and then we need to choose between the level of consistency and the level of availability, right? If you don't know what CAP theorem is, or if you have not watched my previous video on CAP theorem, please go back and watch that. It's very helpful. It will help you understand what CAP theorem is and why CAP theorem exists. Okay. And in the end, we will talk about real world applications of CRDTs. Real world applications. First one is collaborative editing. We have talked about it so much in this video that it must be obvious by now. CRDTs are prominently used in collaborative editing systems, ensuring that changes made by different users are correctly merged. This allows for seamless collaboration without conflicts. Next, geo-distributed databases. In databases that span multiple geographic locations, CRDTs play a crucial role in maintaining consistency in the face of network partitions. They enable distributed systems to handle updates across various regions. And if we talk about an additional use case, it is conflict-free data merging. CRDTs are employed in various scenarios where conflict-free data merging is also crucial, like version control systems. Okay. So that's it. I hope this, after watching this video, you know how Google Docs work. And now if somebody asks you about the system design of Google Docs, maybe you can throw some lights on the CRDTs also along with other components of the system. You can tell them you know how Google Docs handle conflicts and how it resolves them. So yeah, please let me know in comments if you like this video. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.